Warning, the video you're about to watch contains mathematics at the level of Precalculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant as a review for those students who are enrolled in a pre-calculus course covering equations. Well, this review covers equations. We're going to just talk briefly about the whole idea behind solving equations in mathematics. You should already have been pre-exposed to solving all different types of equations. In fact, I have a whole list of them right here. Radical equations with even indices and odd indices, honestly. Rational equations, exponential equations, logarithmic equations, trigonometric equations, linear equations, quadratic equations, cubic equations, absolute value equations, right? The list goes on and on and on. You should have no questions on how to solve those types of equations at all. However, I always find it's very nice to have a roundup of what it means to solve an equation and kind of tactics you're always looking out for as you solve an equation. You could pause the video and read these two paragraphs if you want, but the gist of it is this. You really just have to pay attention to the domain and range of functions as you solve equations. For most equations, there's just a simple tactic. Isolate x. That's pretty much all you need to do. However, certain kinds of equations require special techniques. For example, polynomial equations, they have several versions of x, right? They could have an x to the first, an x to the fifth, and an x to the 23rd or something like that. And isolating x in those equations would be very, very challenging. So this video is not dedicated to those special techniques. Instead, this is just talking about the domain and range restrictions and how to take those into consideration as you solve equations. As a quick side note, if you're one of my students in my pre-calculus class, this material is in a section in which I do not assign a homework. That is because you're going to be running into equations for the rest of this course. There's really no need to have a single section dedicated to equations. You can refer back to this video as needed to fill in whatever gaps you might have in your knowledge base. Just know it's here. All right, so let's talk about the functions that we normally see within equations and their domain and range restrictions. For example, radicals. If you have an equation that has a radical within it, so let me go ahead and write one up above. Why not, right? The square root of x plus 7 is equal to -2. It's a silly little equation you would solve in Algebra 1, and you couldn't even solve it, and we'll talk about why. But notice the index on that is even. If you don't see an index, it's because it's assumed to have a 2 there. If it was a cube root, it would have a 3, and so on and so forth. So these types of equations, their domains are restricted. That is, the domain of this function we're looking at right here, written as an expression, is restricted. Its argument must be greater than or equal to 0. So just take that into consideration. When you see an equation, you're always looking at all the sub-functions within that equation and saying to yourself, okay, before I solve this equation, I need to note off to the side that x has to be greater than or equal to -7. That restricts the argument of that radical to be 0 or greater. The second thing you need to be aware of is the range restriction of that given function. We know that even indexed radicals cannot return negative numbers. That is, that square root of x plus 7 cannot return a -2. So solving this equation is actually pretty quick. There is no solution. The reality is that square root can't return a negative. There's no need to move. And this is why I am telling you from the get-go that when you're faced with an equation, start by stating the domain restrictions of all the functions within that equation. And then once you make notes of those domain restrictions, x being greater than or equal to 7 here, then you move on to, well, what are the outputs restricted to be? And that might immediately tell you there's just no solution, as we got here. The next kind of equation that's super popular in mathematics is a rational equation. Rational equations are equations that have ratios of functions. So it could be something very simple like 1 over x plus 2 is equal to 3, or it could be something complicated like that. In both cases, you're kind of asking the same question. You know the denominator must be non-zero for rational expressions. So when you look at this first fraction in this more complicated equation, you know that denominator cannot be 0. So you start by saying that. Once you have noted that that denominator cannot be 0, you move to the other one and just state, well, this one can't be 0 either. You also have other functions as these denominators. For example, a logarithm cannot take a negative or a 0 number as its argument. So that argument within the logarithm, this piece right here, which we'll talk about momentarily, has to be strictly greater than 0. Also, the radical, the argument for the radical, which we would call a radicand, that must be also greater than or equal to 0. In this case, technically it can't even equal 0. But these are how I kind of approach all equations. So I just start breaking it down very simply, stating to myself, what are the domain restrictions that we're dealing with? Because then that limits the possibilities for our answers. Another thing that you have to note is that with rational equations, that's actually what we're talking about in this portion right here, there are no range restrictions in general. There could be range restrictions if you have very weird situations, but for right now, basically by themselves, rational equations do not truthfully have range restrictions. Now, a mathematician watching this might say, yes, but 1 over x does have a range restriction because it can't have an output of 0. You're absolutely correct. It cannot have an absolute output of 0. However, that's sort of a special case, so I don't really worry about it when I do a review. Exponential equations. We know that for an exponential function, you could plug anything in for x that you want, so there's no domain restriction when you're handed an exponential equation. However, exponential equations must be positive. Now, again, this is one of those cases where somebody might say, wait, that's not always true. It doesn't have to be positive. Like, for example, what if you're dealing with a negative 2 raised to the x is equal to, I don't care, a negative 37 or something like that? You're right. The exponential function on the left-hand side there can actually return negative numbers. However, once you start isolating that negative 2 to the x power, you can see that it becomes a positive 2 to the x. And again, we're back to the original statement that the outputs of that function must be restricted to be positive. This ends up being critical if you were originally handed something like this, where it's negative 2 raised to the x power equals positive 37. When you divide both sides by negative 1, you get to this, and now you know there's no solution to this equation without even solving. Let's see what else we're considering here. Well, after you talk about exponentials, you're always going to talk about logarithms. That's just kind of how they work. They go in that order almost always. So let's talk about logarithmic equations. Logarithmic equations are equations of the form log base b of some argument plus or minus log base b of a different argument is equal to some number. Now, they're not always in that form. I'm just giving you a general form you often run into. The whole point here is that the arguments of these logarithms must be positive. So right from the get-go, I'll make those notes to myself if I'm solving an equation. For example, if that first logarithm had an argument of 3x plus 7, because I know that the argument of a logarithm must be positive, I would quickly note to myself at the beginning that 3x plus 7 has to be greater than 0, which would imply that x would have to be greater than negative 7/3. No matter what, when I get to my final answer solving this equation, I will check that whatever that answer is greater than negative 7/3. If it's not, I throw that answer out. It's called extraneous. Otherwise, You don't really have too much in the way of restrictions when it comes to the range of logarithms. They can have any number as their output. So this number on the right-hand side here is not really much of a consideration for me when I'm solving a logarithmic equation, because again, logarithms can return any number. So you can see kind of the pattern that I'm going through here. I'm just basically saying, handed an equation, check what the inputs can be, and then check what the outputs should be. That can really limit the amount of time that you need to work on a problem. Now, as you move through mathematics, you get into a subfield of mathematics called trigonometry. Trigonometry is a beautiful subject, and you should already have had a full semester of trigonometry behind you when you're in a pre-calculus course. So all the things I'm about to mention about trig functions should be very familiar to you. If you're handed an equation involving sines or cosines, well, sines and cosines can take anything as their argument, so the domain of each of those is all real numbers. You don't have to worry about that. But the range, on the other hand, is very limited for sines and cosines. It can only return numbers between -1 and 1 inclusive, inclusive, including -1, including +1. Often that's a very fast way to find out that there's no solution. If you have something like sine of 3x is equal to 1.1, you know there's no solution because the sine will never return a number greater than 1. Again, just trying to give you fast techniques to solving equations. Then you get into the reciprocal functions, the cosecant and the secant. They both have the same domain or range restrictions, actually. They are restricted to be between -infinity and -1, including -1, and then 1 to infinity, including 1. So if somebody asks you to solve secant of theta is equal to 1/2, you know there's no solution because the secant cannot return anything between -1 and 1. The domain restrictions on these are a little more convoluted, and usually I would like to wait on talking about that until we do a review of trigonometry. But the reality is cosecants, secants, and actually tangents have incredibly strict domains. So you're always looking out for these domain restrictions when you're dealing with the cosecant, secant, and tangent. Just be aware of that. It does creep into play in calculus. In fact, in Calc 2, when you are integrating over intervals, you do have to concern yourself with the domain restrictions because you might be doing something called integrating over a region, which includes the domain restriction, which is a big no-no. Just to be complete here, the tangent, by the way, has a range of all real numbers, so that's never really an issue. So does the cotangent, but the cotangent also has domain restrictions. Again, I reserve that conversation for a review of trigonometry. Finally, I just want to talk about the absolute value. Equations involving absolute values are really, really popular in calculus. And that's mainly because you're doing something called epsilon delta proofs. You do need to know about how to solve absolute value inequalities and how absolute values work. The arguments for an absolute value can be anything you want, so that is never really consideration. However, the outputs for an absolute value must be non-negative. They could be 0, but they can't be negative, which allows us to solve some absolute value equations very quickly. If there was an exam I was working on and somebody handed me this equation, I immediately know the solution doesn't exist, mainly because an absolute value will never return a negative number. In previous semesters, I would never have done an example in this video. And the main reason is because this is supposed to be a 30,000 foot view of what equations are and kind of things you should think about when solving equations, but it's not really supposed to be like, okay, here's a bunch of examples. However, I do have 2 examples in this video to really kind of align to what we've been talking about. So we're faced with an absolute value equation here. Solve the equation. Absolute value of the square root of x plus 5 minus the square root of x minus 5, and absolute value is equal to 5. You should recall from your college algebra material that the absolute value function is a piecewise defined function. The absolute value of something, well, if that something was already positive or at least non-negative, then there's no reason to have the absolute values and you could rip them off. There we go. So if that happy face was already positive, you could just take off the absolute values. However, if that happy face happened to have been negative, the absolute value is going to force it to be positive by putting an opposite sign in front of that happy face. That will force that happy face to be positive. It's currently negative. You put a minus sign in front of it, it will now be positive. So that's a piecewise defined definition of the absolute value. It's actually the true definition of the absolute value. So using that definition here and noting to ourselves, well, I know that the absolute value must return a non-negative number. Well, here it is. We don't have to worry about that restriction. I also know that within my absolute value here, I have some radicals, and they're even indexed radicals, which tells me that the arguments of those radicals must be non-negative. When I write this down, I try to write it in a color that will stand out to me. So I'm going to say that x plus 5 in red here must be greater than or equal to 0. That is, x has to be greater than or equal to negative 5. And on the other hand, x minus 5 also has to be greater than or equal to 0, which implies that x has to be greater than or equal to 5. So both of those conditions must be true. And if you look at both those conditions simultaneously, there is one of them that outdoes the other. This first one tells us that starting at negative 5, I know my solution lies somewhere in this region. However, the second inequality tells me that x also has to be at the same time greater than 5. Well, if you take a look at those two intervals, it really is that x has to just be strictly, or I shouldn't say strictly, should be greater than or equal to 5. That's the one that kind of encapsulates both conditions simultaneously. Now, I haven't even started solving. I've just written down some restrictions so that I can look back at those when I get to an answer. So let's go ahead and start. If that radical, the argument of the absolute value, if that's greater than or equal to 0, well then, according to our piecewise defined definition of the absolute value, we know that if that argument was already positive, I could just take off the absolute values. So let's go ahead and do that. We get down to this bad boy right here. So all I did was say, if the argument of our absolute value was already positive, you could erase those absolute value signs and you could solve the resulting equation. Solving this radical equation, let's isolate the first radical there. So we get the square root of x plus 5 is equal to 5 plus the square root of x minus 5. All this should be very familiar. Square both sides. Maybe I should use implication signs the entire time. Subtract x from both sides and add 5 to both sides, and then subtract 25 from both sides. And there's no need to actually do anything else here because you need to think as you solve equations. Each step of the way, once you've isolated something, you should look at this and say, is there any solution to this? That is an even indexed radical on the right-hand side, and it's positive. Therefore, it can only return non-negative values. Unfortunately, the left-hand side is already negative. There's no way for 10 times the square root to ever become negative. So this specific branch does not have a solution. So we then zoom out here and we say, okay, well, that was the if the argument was of our absolute value was positive. Now let's worry about what if the argument of our absolute value is negative. In that case, according to the definition of the absolute value, I could rip off the absolute value signs here, but if I do so, I'll have to put an opposite or a minus sign in front of that entire argument because I'm forcing it to become positive. That's what the absolute value will do. I want to force this negative value here to become positive. So we're going to solve the opposite of the square root of x plus 5 minus the square root of x minus 5 is equal to 5. Rather than distributing that negative, I'll just multiply both sides by a negative 1. And again, isolating one of the radicals. And finally, squaring both sides. And I shouldn't say finally because there's still a lot of work to do. Subtract x from both sides, add 5 to both sides, and then subtract 25 from both sides, and you get. Pausing for a moment to check to see if this is realistic, You can see it will be realistic once you divide both sides by -10, because you'll get positive 3/2 is equal to the square root of x minus 5. That can absolutely happen here. Let's go ahead and square both sides and then add 5 to both sides. Now, before you start rejoicing that you actually found a solution, remember you're dealing with radical equations here mixed in with actually absolute value equations. So you need to check your solution. If you go back to the original equation and check this 29/4 to see if it's actually a solution, you would get the absolute value of the square root of 29/4 plus 5 minus the square root of 29/4 minus 5 and absolute value. And we want to know, is that equal to 5? Well, let's do a little bit of arithmetic now. Again, just asking the entire time, is that going to be 5? Reducing down, we get to this, which is the absolute value of 2. And we know that's not equal to 5. So there actually is no solution on this branch either. When I say branch, I mean when you break the absolute value up into its positive and negative cases. So that's a really good example. It really goes through several of the solution techniques that I mentioned previously, looking out for domain and range issues. The next thing I want to talk about, in fact, the last thing I want to talk about, is the discriminant. This comes up peripherally quite a bit in Precalculus, and you should be familiar with it from your previous courses. Given a quadratic expression of the form ax squared plus bx plus c, where a is non-zero, the discriminant is defined to be the value of b squared minus 4ac. That b squared minus 4ac right there should be incredibly familiar to you. That is the radicand of the quadratic formula. So if you had set this equation, or sorry, this expression, equal to 0 and solved, the radicand, the stuff underneath the radical, would have been b squared minus 4ac. Again, solving that quadratic equation, if we had it, we would get this, and there is that discriminant. If that is negative, we know there's no real solutions to our given quadratic equation. And in this case, really, we were not handed a quadratic equation, but it still aligns with that. So just defining b squared minus 4ac as the discriminant allows us to have something that we can commonly talk about. Oh, your discriminant is negative, so don't worry about solving. That type of thing. It just makes it faster. Now, as I mentioned, discriminant is especially useful in determining if a given equation that is quadratic in form has a real solution. When I say quadratic in form, it just means that you have a trinomial where the highest degree term, or the term with the most power, I guess you could say, has a double power of the middle term. Sort of. You can read this, pause the video and read this if you want, but all this should be strongly familiar to you. Now, this statement right here is a little bit of a misnomer. I modified it prior to printing out the PDF, and now that I'm looking at it, it's actually not right. So I modified it. The reason why it's not exactly correct is because when you have higher powers, there are other considerations. But the main thing is, if you have a quadratic equation, ax squared plus bx plus c is equal to 0, it has no real solutions if the discriminant is negative, one real solution if the discriminant is 0, and two real solutions if the discriminant is positive. The most important statement there is the no real solutions part. By the way, some texts, and when I say some, I actually mean pretty much most textbooks, go a little further with this theorem by stating when the solutions are rational or irrational. However, this extra bit of information is often of little use when you're already considering the discriminant. Generally speaking, you're considering the discriminant because you want to throw out the possibility of having to actually solve the quadratic equation. And as a heads up, imaginary solutions are actually important. Very, very important. They just don't become important until you're in engineering or in differential equations. So here's a somewhat silly equation that I created. We have a bunch of stuff equaling 0. Well, that bunch of stuff is actually using this zero factor property, which basically says if you have two objects multiplying, this object and this object, and their product becomes 0, then one of those two objects has to be 0. It's basically my way of sneaking in two problems at once. Now for education purposes, let's solve this factor equaling 0 first. This equation is quadratic in form. You may not see it, but it totally is. The reason why it's quadratic in form is because x to the 1/2 is the same thing as x to the 2/4. And notice the power on that first term is double the power of the second term. And because of that, this is quadratic in form. You can do something called a U substitution if you want to. It becomes incredibly helpful to use U substitutions as you move forward in mathematics, specifically in calculus. So if you let U equal x to the 1/4, then U squared is equal to x to the 2/4, which will imply that our given equation there can be rewritten as U squared minus U minus 6, which is totally factorable. Once you factor that, again, you face another zero factor property. That is, you have two objects multiplying to become 0. So therefore, either the first object is 0 or the second object is 0. And that implies either U is equal to 3 or U is equal to a -2. Now here's the big deal. When you're in calculus, you want to make sure that you resubstitute back into the world or the variables that you were originally using. We were not in the world of U's to begin with. We were actually in the world of X. So let's go ahead and resubstitute back into the world of X. We just use this substitution into the world of U to make things visually appealing. But in reality, U is just x to the 1/4. So I'm going to trade those U's out for an x to the 1/4. Every step along the way, you should check for realism. These 1/4 powers, you should recall, mean the 4th root of x. And if you're looking at an even root of x, then you know that x, first of all, has to be non-negative, but you also know that its range, its output, also has to be non-negative. And that's a problem right here. I have the 4th root of x equaling a negative number. That can't happen. So that's called an extraneous solution. We get to cross it out. It does not exist in this situation. Moving forward, we still need to solve for x on that first equation there. So let's raise both sides to the 4th power to unlock x. And we get that x is equal to 81. So that is one solution. It's a good idea as you go through solving large equations like this, that you write out your solutions in a clean area. So that's what I'm going to do here. I'm just going to list all of my solutions over on the left-hand side of my paper. All right, so we have now solved at least the highlighted part equals 0. Now let's move on to the other factor equaling 0. That is, we're going to solve 2 times 9 to the x plus 2 times 3 to the x plus 1 equals 0. Now the thing about this equation is it often throws people off because they don't know how to solve it. It is quadratic in form, believe it or not. You just have to rewrite 9 as 3 squared. So that's what I'm going to do off to the right-hand side. And now I get to use a law of exponents to go ahead and rewrite this 3 squared raised to the x as 3 to the 2x. Believe it or not, that is quadratic in form. If you look, this 3 to the 2x right here is double the power of 3 to the x. If you don't believe me, do a U substitution. It is sort of illegal to do another U substitution within this problem. We've already used the letter U. But let's call this, if you're into programming, a local variable. So in this case, we'll just pretend as though U is locally defined to be U equals 3 raised to the x. And that will imply that U squared is 3 to the x squared, which is 3 to the 2x. And so our black ink right there can be rewritten as 2 times U squared plus 2 times U plus 1 is equal to 0. Now I have a quadratic equation that I would love to solve, but this is one where I'm just going to showcase how to use the discriminant to your advantage. The discriminant here is b squared minus 4ac. Remember, that's a, that coefficient is b, and this constant is c. So b squared minus 4ac, or the discriminant, is equal to 4 minus 8, or a negative 4. And I immediately know there's no point in me finishing out this problem because there's no solution to that quadratic equation, no real solution that is. Generally speaking, unless you're working in differential equations, or if you're working specifically in a section where they say we want imaginary solutions or all complex valued solutions, you would stop when the discriminant is negative for an equation quadratic in form. So in the end, that ugly looking equation has just one solution, 81. That's it. That turns the second factor, this guy right here, into 0. And then 0 times whatever it turns the other factor into will still be 0. Now I understand that if you're using this video to review how to solve things, it's not super helpful. But that's not the intent of this video. This video is meant to give you a way to think about how to use all your solution techniques and speed them up. You're supposed to look at an equation, determine immediately what are the viable values of x that you could plug in, and also use the given functions within the equation to determine realistic outputs. That will allow you to throw out solutions very quickly. All right, we're done with this video. I hope that it helps, and I hope to see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.